Jessica got her PhD from the University of Michigan, and then she was an IMPS fellow at UC Santa Cruz, and now she is still Santa Cruz as a Hubble fellow. So today she's going to tell us about the gas around galaxies.
Thank you. Thank you for having me here. I would like to start with a portrait of a galaxy. A galaxy is not a quiet, uneventful place. Most were born violently and live in a constant state of turbulent complexity and upheaval. A galaxy, like the Milky Way, maintains a complex ecosystem in which baryons cycle through many physical phases, from stars, interstellar medium, dust, to intergalactic medium. Galaxies drive large-scale winds. Wind-related feedback processes are the dominant feedback mechanism driving galaxy evolution and formation and are key to the thermal evolution of a galaxy and its interstellar medium. Galaxies also accrete gas. And accretion is the means by which a galaxy survives for several billions of years. Together, the two mediate galaxy evolution and are inextricably tied to the physics behind star formation, quenching, and the existence of a circumgalactic medium, which is what I will focus on today. The circumgalactic medium is loosely defined as gas within a virial radius of a galaxy bound to the dark matter halo. This is diffuse, ionized gas, and it is where accretion, feeding star formation, meets enriched feedback materials. It's where satellites are stripped and disrupted, and it is where ejecta may eventually be recycled. By way of introduction, I would like to point out that even without observing winds and accretion and the circumgalactic medium directly, we can actually infer their existence from very well-known galaxy properties and global scaling relations. First, compared to the cosmological baryon fraction of 17%, galaxies appear to be severely baryon depleted. At about the mass of the Milky Way, it turns out that this relation of the fraction of baryons in galaxy halos reaches a maximum of about 25% when you consider the amount of baryons in stars and gas in the disk. And so this relation is often attributed to powerful outflow mechanisms. It may also imply the existence of a circumgalactic medium. So the most basic observation that there are two types of galaxies in the universe cannot be explained without discussing gas supply and gas consumption. Recent years have brought tight constraints on the growth of the red sequence from Z of 2 to Z of 0.5, implying that some star-forming galaxies have shut off their star formation and evolved onto the red sequence. And so the means by which this transformation from blue star-forming disks to quiescent spheroidals happens is absolutely related to the evolving balancing act between gas supply and gas consumption. The mass-metallicity relation, which extends over 3 orders of magnitude in stellar mass and over all redshifts as far as we can tell, which is the relation between the galaxy metallicity, either gas phase or stellar, and the stellar mass of the galaxy, absolutely cannot be explained without inflows and outflows, which many authors have remarked on. I think one of the most interesting things to come out in recent years is work by Gibran Zahid, who is here, and Molly Peebles, who have determined that when you count up all of the metals in a galaxy within its stars, within its interstellar medium, and compare that with the amount of metals that it should have generated based on their stellar content, galaxies are missing over 80% of the metals that they've generated over the course of their lives. This is, I think, striking evidence that they must lose these metals somehow, drive massive outflows. They must be somewhere, perhaps, in a circumgalactic medium. One of the oldest arguments for gas accretion, the need for gas accretion in galaxies, is the so-called G-dwarf problem in the Milky Way. And this is simply that the distribution of metals that you observe in the solar neighborhood of G-dwarf stars is actually quite tighter than what should be if you just had closed box evolution. And in order to reproduce the observations, you require metal pore inflow. the Kennicut-Schmidt law, which we all know and love, which is a relation between the gas surface density in a galaxy and the global star formation rate surface density, appears to hold across many orders of magnitude over many redshifts from quiescent disks to star-bursting galaxies. And the thing is that the rate of star formation and the star formation of history of most galaxies has been fairly constant over their lifetimes. That implies a constant gas surface density. But at the current star formation rates of most of these galaxies, they exhaust their gas supply in way shorter than a Hubble time, usually about 2 gigayears. So what this requires is gas inflow. And many authors listed here note that the Kennicut-Schmidt law, its existence, requires inflows. And finally, the evolution with time of the cosmological mass density of neutral gas cannot be explained without inflows. The value is at least a factor of 2 higher at redshift 2 than at redshift 0, but at redshift 0, there's about twice the amount of baryons locked into stars at redshift 0 is about twice the amount of gas that's supplied by these high redshift DLAs, which therefore implies that galaxies have to be replenishing gas before the present epoch at a rate that's similar to their gas consumption. So, not only can we infer these from winds and accretion and a circumgalactic medium from these well-known galaxy properties, but there are direct observations of these phenomena. Winds are observed over many wavelengths for many galaxies, including our own Milky Way, which is driving a star formation-driven wind into the halo, massive amounts of material. This is observed, these radio lobes emanating from the galactic center. You see winds around M82 and other galaxies and X-rays. You see winds around normal star-forming galaxies and molecular gas. Almost everything you see when you observe a wind is a direct result of the interaction of the wind fluid and radiation with an ISM and an ambient medium, say the circumgalactic medium. And the properties you derive from the wind actually depend on the observed phase. Gas accretion is also observed. The observations are a little less direct. One of the observations that I like the most is the sort of lagging rotation. So this is a rotation curve of H1 gas for NGC 2403. This is a normal star-forming galaxy. And all this stuff here is H1 gas that is lagging behind the rotation of the normal H1 disk. And you can fit some very simple models to this and determine that the vast majority of this gas is actually accreting onto the galaxy, and 20% of it has to be accretion from the intergalactic medium. The high-velocity clouds, this is a map of the high-velocity clouds in the halo of the Milky Way. They're roughly within about 20 kiloparsecs at most, appear to be moving through a hot medium. They have this head-tail structure. The Magellanic System in our own halo at about 50 kiloparsecs will ultimately provide 10 to the 8 solar masses of fresh fuel for the Milky Way. And Kate Rubin has pioneered a technique where you look down the barrel of galaxies that are edge-on, and you can actually see accretion happening in warm ionized absorption. This is metal-enriched accretion, redshifted from the galaxy's systemic absorption. So, there are also observations of the circumgalactic medium, which will be the primary focus of this talk. Most of the direct observations that I've talked about are within the inner, say, 20 to 30 kiloparsecs of a galaxy. The medium through which these processes propagate is both shaped by and comprised of winds and accretion, and it's the medium through which these processes, winds, outflowing gas, and inflowing gas, must move. So the thing about the CGM is that it's very diffuse, it's very ionized, and you have to observe it via absorption. There's no way to look at it with current instrumentation and emission. And so we devised these experiments to look at it where we have a bright background source, typically quasars, although some people use bright background galaxies, and a galaxy in the foreground, and that quasar will pierce the circumgalactic medium of a foreground galaxy. You'll point a telescope at the quasar. You'll associate absorption along the line of sight of the quasar with the galaxy, knowing the galaxy's exact redshift. I'll show you a little bit more about that experimental design as we go on. So the structure of this talk is, first I'm just going to talk broadly about the circumgalactic medium, give you a tiny bit of history. And then I'm going to move on to what we find in our survey of halo gas called the COS Halo Survey. I'll talk about the survey design, and I'll talk about just some direct results from these data that we've collected. And I'm going to spend the last 20 minutes or so talking about two puzzles that emerge from these data in terms, two puzzles that really require theoretical input. They keep me up at night, and I don't have any answers for these, but I would love to hear any suggestions that audience members might have. The first is a quenching mystery and involves the cool gas around elliptical galaxies, and the second one is the physical state of the gas and pressure support, or lack thereof. So back in 1969, John Bacall and Lyman Spitzer predicted that most of the absorption lines observed in quasi-stellar sources, quasars, with multiple absorption redshifts are caused by gas in the halos of normal galaxies. This prediction has been borne out finally. 40 years later, they installed the cosmic origin spectrograph on the Hubble Space Telescope, and I think finally we're really able to test this hypothesis. So the goal is to look at a diversity of galaxies over a range of impact parameters. Because we're limited to absorption line spectra, because quasars are not so common on the sky, we usually have about one sight line per galaxy. So we construct statistical samples where we group by galaxy and accumulate a lot of galaxy-quasar pairs and then make inferences about the circumgalactic medium broadly and generally. Like I said, the gas is very diffuse, and most atomic transitions that are common to the circumgalactic medium lie in the ultraviolet. And so, therefore, because we have an atmosphere, because we can live on the planet Earth, we require space observations, unless we're going to high redshift. But and in high redshift, you can do great work on the circumgalactic medium, but there is some confusion with the IGM. I'm going to talk mostly about the low redshift circumgalactic medium in this talk. So if you're going to design an experiment to look at the circumgalactic medium of galaxies, you can go forward, do it one of two ways. And the first way is what's been done previously because of, just restrictions in terms of how many quasars could be observed with UV instrumentation, and that is you look down the barrel of a quasar, you find absorption lines in the spectrum at a particular redshift, and then you go hunting for a galaxy nearby at that proper redshift. Another way to design a survey is the redshifts of all the galaxies nearby in projection, and then you take a spectrum of the quasar and go hunting in the spectrum of the quasar for absorption at that particular redshift. So method A is what's been done most, but that method is actually highly biased. You're biasing yourself toward finding absorption. If you do it via the second method, then you're actually probing what are the global properties of circumgalactic gas. If there's no gas there, you'll be able to say something about that. I think this plot is supposed to illustrate to you that the cosmic origin spectrograph was really a game changer for circumgalactic medium studies. STIS is a great spectrograph, but it's less sensitive to ultraviolet light than COS. COS is about 100 times more sensitive, which really opens up a large fraction of the sky. It allows you to design surveys that, via method B, these absorption-blind, galaxy-based surveys, which really weren't possible until the installation of the spectrograph. Okay, so this is meant to show you some of the work that's been done on the circumgalactic medium in recent years. Like I said, there's been a lot of work, great work done at high redshift, quasars probing quasars using Lyman break galaxies. These are always extreme galaxies, extremely star-forming galaxies, or the most massive galaxies that are hosts of quasars. At low redshifts, we've looked at dwarfs. I'm going to focus on COS halos, which is L-star, Milky Way, normal star-forming galaxies. But I don't want to give you the impression that COS halos is the only survey out there looking at circumgalactic gas. All right, so broadly speaking, the circumgalactic medium contains a lot of gas that you can probe via the Lyman series lines. And in particular, when you look at Lyman alpha, I'm going to show you a lot of plots like this. So what you have here is an equivalent width of Lyman alpha, And this is a projected separation in the rest frame of the galaxy where the quasar is in relation to the galaxy. So it's a projected distance, not a three-dimensional distance. And what you can see is that the absorption tends to follow a trend, and right around 300 kiloparsecs or so, you start to get a lot of upper limits in terms of Lyman alpha. But it looks like there's a CGM that's well-defined out to 300 kiloparsecs for most galaxies. And you see here the covering fraction within the virial radius, and this is how this one is normalized here, is approximately 1 for L-star galaxies, almost 1 out to a virial radius for sub-L-star galaxies, and for dwarf galaxies it's a bit lower, but it still exists. The CGM is enriched with metals. The most common way that people have looked at the circumgalactic medium is through magnesium-2 absorption, which I'm showing you here. There's a steeper drop-off with galactocentric distance, with impact parameter, I might say, but there's a fairly high covering fraction of about 70% within 75 kiloparsecs of normal L-star galaxies. Circumgalactic medium is dusty. I really like these results from Brice Menard. Basically, he does this measurement based on correlating the brightness of 85,000 quasars with redshift greater than 1 and the position of 24 million galaxies with redshifts of 0.3 and measuring the cross-correlation between the colors of the background quasars and the distribution of foreground matter. And what you can infer is that there's a large amount of dust, not only in the circumgalactic medium of galaxies, but extending out to megaparsecs from galaxies. But also, if you look at the amount of dust in the halos of normal galaxies, it's approximately the same as the amount of dust that's in the disk of the galaxy itself. There's also an X-ray halo, and this has been a bit more elusive. But there is hot gas. I think Bogdan, who may or may not be here at the CFA, has done some work on this in terms of looking at galaxies with XMM Newton data, where you can see that generally, X-ray emission around galaxies is faint, but you can detect it sometimes out to 60 kiloparsecs. Usually it's only within about 20 to 30 kiloparsecs, but there is a hot gas phase. There's not a lot of baryons in this hot gas phase, though. When you think about the cosmological baryon fraction, and galaxies are missing 75% of their baryons, if you just look at the disk, the X-ray gas really doesn't amount to much. It gives you another maybe 5% or so, 5 to 10%. Okay, so now I'm going to move on to results from the COS Halos survey, which is the survey with which I've been involved. COS Halos was designed as a galaxy-centric survey, so it's designed based on the properties of galaxies. We select L-star galaxies within 150 kiloparsecs of a nearby quasar in projection. These galaxies are both star-forming galaxies and passive galaxies. The breakdown in the sample is about 2/3 star-forming, 2/3 non-star forming. We define this based on the spectrum of the galaxy, so star-forming galaxies have emission lines. Non-star forming galaxies do not. They tend to exhibit absorption lines. We look at galaxies in a very tight redshift range of about 0.1 to 0.35. This is so that we can probe one of the most common transitions of the circumgalactic medium, oxygen-6, which I'll touch on briefly. I talked a little bit about that at the lunch today. And we look at the inner halo. So I said before, and I've shown to you now, that the circumgalactic medium of galaxies extends to 300 kiloparsecs. For an L-star galaxy, that's about the virial radius, or maybe a little more. But we're actually looking at the inner halo. So we probe mostly within 150 kiloparsecs of L-star galaxies. We use the cosmic origin spectrograph, the UV spectrograph on the Hubble Space Telescope, and we also use high-res spectra to get data on magnesium-2. Okay, so this is just supposed to illustrate to you the survey design. So I'm just going to show you a few of these. So you've got a galaxy, you've got a quasar nearby in projection. We know the redshift of the galaxy. See the spectrum? That gives us a very precise redshift to within about 15 kilometers per second. And therefore, we know the projected distance, 15 kiloparsecs. And when we go hunting in the absorption spectrum of the quasar, boom, Lyman alpha right there. There are other transitions as well. I'll just show you some Lyman alpha. But every time we do this, We take a spectrum of the galaxy, get a precise redshift, and we go hunting in the spectrum of a quasar, boom, Lyman alpha. Okay, here's another normal L-star-ish galaxy. We go hunting for Lyman alpha, boom, there it is, boom, there that is. Okay, so I could do that for probably every single sight line in the sample. Most of this gas is bound. When you look at the profiles of the absorption lines, you find that that most of the gas, so these are the centroids now of the strongest component in the Lyman alpha absorption, and this is galaxy systemic. So this is in the rest frame of the galaxy. Right here, I'm just showing several values of the escape velocity from a normal L-star galaxy. And what you see is that most of the absorption, and this is the total extent of the absorption, is well within the escape velocity from an L-star halo. So this gas is bound, probably. Okay, so when we look at the H1 in bulk, what we see here, this is now the equivalent width of Lyman alpha. This is a column density of Lyman alpha, if you prefer. This is calculated by the apparent optical depth method, for those of you experts in the crowd. And what you can see immediately is that almost every galaxy in the sample has strong Lyman alpha, up to an angstrom here, an equivalent width, with a typical column density of about 10 to the 16, 10 to the 17. We have a lot of saturation, so that's why these arrows are here. So these are lower limits on the total column density of H1 and the halos of these galaxies. I think one of the things that I'm going to come back to is that there's really not a significant difference between the Lyman alpha of red galaxies and the Lyman alpha around blue star-forming galaxies. There are some red galaxies that don't seem to have it. Maybe it's a bit patchier. But by and large, the red galaxies have just as much H1, cool gas around them, as the blue star-forming galaxies. Okay, so just empirically, the circumgalactic medium is a multi-phase medium. Okay, so you can deduce this. You've got H1. We probe many ionization states of different heavy metal lines. We've got carbon-2 here. We've got carbon-3. Carbon-3, the third ionization phase of the metal lines, is always stronger than the second. We've got nice magnesium-2. You never see nitrogen-5, which I talked about at lunch. That's a puzzle. Sometimes you see alignment between the oxygen-6 and the lower ionization states of lines kinematically. Sometimes you don't. Sometimes it seems very offset kinematically. Maybe over the same broad velocity range, but it looks like oxygen-6 is tracing a distinct phase from the lower ionization state lines. So these low ionization state lines, like I said, you've got silicon-2 and you've got silicon-3, and this plot is just meant to show you that we have about a 70% covering fraction to 150 kiloparsecs, and 90% for silicon-3 or carbon-3, the higher ionization stage. That's just telling you, and I'll show you another plot on this, but the gas is ionized. You can deduce this just from, the empirical relations alone. The gas is highly ionized. Even the cool 10 to the 4 Kelvin gas, we think this is photoionized gas. Okay, the high ions tell a different story. The oxygen-6 now, if you look at this, you can see there's actually a distinction between the red galaxies and the blue galaxies. And it turns out that the strength of oxygen-6, now column density, is correlated with the star formation rate of a galaxy, and that more strongly star-forming galaxies tend to have stronger oxygen-6 in their halos. So this dichotomy, the general dichotomy in the galaxy population between red and blue galaxies, seems to be reflected by the presence or absence of oxygen-6 in the galaxy's halo. And this particular puzzle I discussed today at lunch, so I'm not going to go into it, but if you're interested, let me know. I'm happy to talk more about it. This, again, is just telling you that the gas is ionized, highly ionized. So we've got the silicon-3 state and the silicon-2 state. Just from these adjacent ionization states of metal lines, you can infer a rough ionization parameter and figure out that most of the gas, probably 99.9% of the gas, is ionized. Okay, so now, in the final 20 minutes that I have, I want to talk about some of the implications of these results and some analysis. And so the circumgalactic medium is almost definitely linked to the physics behind galaxy quenching. If it's a lack of cool gas flows that terminate star formation in galaxies, then the circumgalactic medium would presumably reflect this. if instead the interstellar material of quiescent galaxies was somehow rapidly ejected into its surroundings, the circumgalactic medium may reflect this. If there's some mechanism keeping galaxies dead, preventing gas accretion, the circumgalactic medium could reflect this. So I recently went to a conference all about quenching and quiescence, and I learned that there are many ways to quench a galaxy and to keep a galaxy from accreting gas. But in general, the main point here is that most models of quenching and quiescence seem tuned to keep gas from cooling onto the galaxy. But we found that cool gas around galaxies abounds, that there is a lot of cool gas, and I'm going to go into that too, more specifically. So if we follow the gas, we might be able to say something interesting about quenching. All right, inside of elliptical galaxies, there seems to be some gas. This might be a failure of maintenance mode. It's not forming a lot of stars. But again, like I said, there is just as much gas outside of the cool gas outside of red galaxies as there is outside of blue galaxies. And so one of the things I hear a lot about this, because we do have a small sample of red galaxies, is that we're not actually looking at the circumgalactic medium of passive galaxies. We're looking at more of an intragroup medium. So there are easy arguments against this. First and foremost, the gas is within the virial radius. It's bound. The kinematics of the gas are not consistent with being part of an intragroup medium. And there's a very high covering fraction. I've also heard that, well, maybe this gas around red galaxies is stripped gas from satellite galaxies. And you can actually do these calculations statistically, knowing how many satellite galaxies there should be. And it turns out that the high covering fraction and the line widths, it's just not sufficient. The multiple components along each line of sight, it just doesn't really mesh with the idea of being from satellite galaxies. And of course, the other argument is that, well, you just have a small sample. Maybe you just got lucky in terms of the red galaxies you chose having gas outside of them. But I'm just highlighting here work from Guangtun Zhu, who's a Hubble Fellow at Johns Hopkins, who studied luminous red galaxies at a redshift of 0.5 in a similar way using SDSS data and stacking quasar spectra. And he finds a huge amount of magnesium-2 around luminous red galaxies. So I think it's a generic feature of galaxies that are not forming stars, so-called quenched galaxies, that they have a lot of cool material in their halos. And this is actually in direct contradiction with many theoretical predictions. One in particular that I would like to highlight is work by Kyle Stewart. And one of the reasons I'm highlighting it is because he made these lovely predictions for the H1 covering fraction around galaxies. And so at around this so-called transition mass of 10 to the 12, a halo mass of 10 to the 12, there should be a precipitous drop in terms of the covering fraction of H1. So the observed covering fraction that we see within 160 kiloparsecs is 90 plus or minus 5% for all galaxies, including red galaxies, which is directly at odds with these predictions. And so I understand that newer simulations don't feature this transition mass where between cold mode accretion and hot mode accretion. I think that's great. One of the things, though, that has to be is that if there is so much cool gas around passive galaxies that is not accreting onto the galaxies, and it's not part of some dynamic baryon cycle within galaxies being ejected and returned to the disk of a galaxy or the sphere of a galaxy, that gas has to hang out there then for a long time for us to see it. And so now I'm going to talk a little bit about the physical state of the gas and what we can infer when we do some photoionization modeling in terms of the density, the mass of gas that's out there. And I'll end with a mystery on pressure equilibrium. So like I said before, you can look directly at the ionization states of the gas, compare their column densities, and know that the gas is highly ionized. But in order to do that properly, to get a proper ionization correction for the gas, that is, convert H1 that you see in Lyman alpha to a total hydrogen, where most of the hydrogen is ionized and unobservable, we don't have any transitions for ionized hydrogen, you have to do detailed photoionization modeling. So luckily, I showed you data where we have many ionization states, many adjacent ionization states of heavy metal lines where we can actually do this. Silicon 3 to silicon 2, independent of metallicity or subsolar ratios of metal lines, gives you a great constraint on the ionization parameter. Carbon 2 to carbon 3 also. And actually, it turns out that when you model these COS halos data with all of the available transitions, you can get a pretty consistent result for the ionization parameter. You can also, it turns out, get a gas metallicity from photoionization modeling if you get a total amount of hydrogen gas and you have metals, correct for total metals. But unfortunately, this correction is a lot less robust than the ionization parameter. I would say the ionization parameter is uncertain to maybe within a factor of 3. The metallicity is uncertain to probably within a factor of 10 that comes out of these models. And mostly that's just a product of our data. Our data, many of these absorption lines are saturated, so they are lower limits. And that's fine if you're making an estimate of the total amount of mass in the galaxy halo, because then you can just give a lower limit for the total amount of mass. Many of the metallicities that we get are actually upper limits, by contrast, and many of the upper limits we get are something like solar. So when we can get a good metallicity for the gas, it turns out to be about 0.1 solar. This gas is metal enriched. We're working on getting better metallicity estimates, so stay tuned for that. But basically, the method is, like I said, now bear with me on some of these plots. So this is log the column density of a particular ion, where the color of the line corresponds to an ion. Okay, on this plot, I've got the ions listed up here, but what you can see is where I've constrained the ionization parameter to lie. And I give a really big range. So there's a lower range and an upper range in terms of what's possible. So let's look for a minute at silicon. In this case, you've got silicon 2 here, and the bold place is what we measure. The line here is the line from cloudy at this particular H1 column density and this particular metallicity. And what you can see is that silicon 2 and silicon 3 match up right about here at an ionization parameter of -3.5. That corresponds to about 99.99% of the gas being ionized. You can see also that nitrogen 2 and nitrogen 3, they give a slightly higher ionization parameter, but they're consistent with this range that I've defined. And so you can do this for all of the sightlines in the COS halo sample and get out ionization parameters for each sightline. And it can be somewhat taxing, but you can do it, and then you can get this range of ionization parameters, which is shown here. And now I've parameterized to the virial radius, R over R vir. And so, like I said, there's large degree of uncertainty. So when I go to make a mass estimate for the total amount of gas, I want to be conservative, especially in the context that baryons are missing from the halos of galaxies, as we found them by looking at the lower ionization state gas. So what I'm going to do is be as conservative as possible. I'm going to choose the lowest ionization parameter that I can, that's allowable by my analysis. I'm also going to choose the lowest allowable H1 column density. These are lower limits, they're saturated, but I'm going to choose that lower limit. And I'm going to make the corrections for the total amount of hydrogen in the halo of the galaxy. So what you see here is now not H1 as a function of the projected distance from the galaxy, but the total hydrogen. Okay? And so I've made the ionization corrections, and you see now that the total hydrogen columns are between 10 to the 19 and 10 to the 20. The ones that are lower limits I show with upper arrows there. There are some that I was unable to do this for. This is the ones where you don't detect metals in the halos of the galaxies. And you see that there's maybe a declining trend with impact parameter. And so when you take this as a surface density of total hydrogen in the halos of normal galaxies, you can calculate a total mass of this photoionized material. And the question is, how does this stack up? And so what I'm going to show you is this plot. This is for the cosmological baryon fraction here is 1. So if, when we include these things, The total over here would reflect 1. The dashed lines are showing just the slop in the measurements. And so in the disk of a galaxy, for instance, galaxies can have anywhere between, say, 15% and 30% of the baryons in the disk of the galaxy. This is the hot CGM here. That's constrained from X-rays. I used Mike Anderson's ROSAT stacks in order to make that. And like I said before, the hot CGM really doesn't contribute much to the total baryon fraction of normal halos. So now let's add in this cool CGM. I told you oxygen 6 is probably a separate phase, so you can make a separate estimate on oxygen 6, a very conservative separate estimate. And when you do that, it turns out that, yes, there's a lot of slop in the measurement. So it appears that including the cool photoionized gas in the halos of galaxies and the warm oxygen 6 gas in the halos of galaxies can close this missing baryon problem on galaxy halo size scales. We find quite a lot of material in the cool circumgalactic medium. And actually, even this hashed region is a conservative estimate. And when we get better H1 estimates, we've gone back to get better data, I'm guessing this might even go up. So I think galaxy halos are not, as far as we can tell, galaxy halos that are L star in size are not missing a significant fraction of the baryons relative to the cosmological fraction. Okay, but now let's talk a little bit about pressure support. So let's ignore the existence of oxygen 6 for a second. In the old picture, or common picture of galaxy halos, you have a hot halo with cool clouds that condense out of it that are in pressure equilibrium with this hot gas. What Mahler and Bullock did in 2004 is they predict a hot gas density profile that evolves adiabatically from a Navarro-Frank-White distribution. And what they do is they predict a density profile for the hot gas, and they predict a density profile for the cool gas that would condense out of this and be in pressure equilibrium with the hot gas. So as far as the survival of the gas is concerned, if you're in pressure equilibrium, you can survive for long timescales in the halos of these galaxies. And that's good if you want to hide a large amount of the baryons in the halos of galaxies. If these wind-related feedback processes are driving a lot of material into the halos of galaxies, if recycled accretion is a big part of how galaxies accrete the gas that they need to keep forming stars over billions of years, you need this gas to be able to stay in the halos of galaxies for, a long time. Otherwise, it doesn't make sense that we see so much of it. And so one of the things that we can do from the data, from the modeling, is get a density profile of the gas. The ionization parameter is simply the ionizing photon flux that you assume, and this is highly uncertain by maybe, a factor of 5, I would say. The slope of the extragalactic UV background that you use matters. Whether or not you include escaping radiation from the galaxy SED matters. Maybe non-solar abundance ratios of the metal lines matters. All of this can contribute, maybe a factor of 3 to a factor of 5 in uncertainty. So that's reflected here by this plot, but here's the density profile that you get. This is the density. So you see most of these cool clouds have a density of about 10 to the minus 3.5 is, say, the average density of these cool clouds. And so now it's easy. We can compare that with the Mahler and Bullock model, the derived gas densities. And what you get is that the cool gas, which is shown here by the white data points, follow the hot gas profile well. To be in pressure equilibrium with the hot gas, they would have to follow this cool gas density profile. They are several orders of magnitude below this, okay? So even allowing for a factor of 5 uncertainty and all of the things that go into the photoionization modeling, which is generous but maybe realistic, you still cannot explain the low densities of the cool clouds with this simple picture of cool clouds in a hot medium. So I actually went a little fast, but I'll go through a summary here. There's ample observational evidence for multi-phase winds and gas accretion and the ambient medium through which they move. I talked about the large quantity of gas in the circumgalactic medium, enough to close the missing baryon problem on galaxy halo size scales. In particular, I'm confused by popular models of quenching that predict a deficiency of cool gas in the halos of massive non-star forming galaxies. And if you propose instead to keep that cool gas out there from falling onto galaxies, it has to stay out there for a long time. And for it to stay out there for a long time, it should probably be in hydrostatic equilibrium, which is, at least we rule out a very simple model in which the cool gas we observe is in hydrostatic equilibrium with an ambient hot halo. And so in the future, I think there's a lot of work to be done on the circumgalactic medium. One of the things is that the redshift range at about Z of 2 to Z of 3 has been probed very well by optical data. The redshift range now around Z of 0.2, Z of 0 has also been looked at, but there's a huge gap in the cosmic history of the universe between Z of 0.4 and Z of 2 that we know nothing about the circumgalactic medium. And this is a very important time in the cosmic history of galaxies. So we actually have several large programs that are doing this right now, targeting quasars at very high redshifts and all galaxies, very, very deep galaxy redshift surveys for stuff in the foreground of these quasars. So stay tuned on that. If you talk to anybody on the future space mission committee being called HDST, I get very excited when I hear about multi-object spectrographs and IFUs in space that are very sensitive. And so instead of using quasars to look at the galaxies, you can use many, many background galaxies to densely sample the foreground gas. So instead of just one sightline per galaxy, you could get a lot of sightlines per galaxy. You can learn a lot more about the CGM of individual galaxies. At some point, we're going to be able to directly image the circumgalactic medium. The surface brightness, like I said, is too low for current instruments, but you should be able to do it. I really enjoyed this particular paper. You can detect the circumgalactic medium potentially through the SZ effect imprinted on the cosmic microwave background. Anyway, there's other opportunities, but I'll stop there. Thank you.
Great, we've got some time for questions.
Yeah, just to give you context, when you take an L-star galaxy, the halo and the disk, what fraction of the baryons are you saying are gas versus stars?
So stars are probably about 15% of the baryons.
15?
15. Mm-hmm.
So that
the rest
star
is
formation
gas.
rate, we can go a long time before.
Wait, with the gas that you include in the halo, sure, yeah, you could go on forever.
Some of us with long memories are not at all challenged by this fact that you've not been able to find support, pressure support, from the hot medium to the cold gas. I mean, those of us with long memories remember that microlensing discovered this 15 years ago, that there's a reason, and that is that these are condensed objects. They have a microlensing signature, and I'm saying, therefore, that what you're seeing, we're doing the same experiment, looking at distant quasar, and we see it with microlensing, you see it with absorption. We see a large population of planet mass objects which are made of the primordial hydrogen. In other words, the dark matter objects. So they're not pressure supported, they're gravitationally supported. No problem.
I'll have to think about that.
You don't have to at all. It's been done a long time ago. They're gravitationally supported and they're seen in microlensing. What's the problem?
All right, Jay.
Is there any additional contribution to photoionization from hot stars in the galaxies themselves, or is it entirely from extragalactic background?
That's a really good question. So, yes, there could be, potentially. I've looked into this. You have to assume some escape fraction. Okay, so if you just take a typical galaxy SED from, say, like Starburst 99, and you assume some normal escape fraction, maybe like 5%, 10%, and you assume that the photoionizing radiation scales with the star formation, scales the star formation over distance squared, so impact parameter squared. then at a typical star formation rate that we probe by COS halos, which is about one solar mass per year, the galaxy SED is a little bit less than the extragalactic UV background in terms of the photoionizing radiation. The slope is actually very similar, so in terms of the ionization parameters that you get out, it's the same. Now, instead, if you want to scale up the star formation for the strongly star-forming galaxies, you could get within about 20 kiloparsecs that could dominate over the extragalactic UV background. But again, the slopes are very similar, so the ionization parameters wouldn't change. The densities would change, but probably by a factor of 5 or something like that. So that's part of what I was allowing for. Now, there's something very interesting, which is what I really like is new work on high-mass X-ray binaries in galaxy disks, which could produce soft X-ray emission that escapes efficiently into the halo and maybe has a peak at about 10 Rydberg, which could be responsible for oxygen-6, well over the extragalactic UV background at 10 Rydberg. And I'm excited by that. I don't know much about it, but I'm still learning. So yeah, it could have an effect, for sure.
I have a question. So where is all the nitrogen 5? Is that a problem, or is that just...
It's not really a problem. So there's no nitrogen 5 around these galaxies, basically. We can put strong limits on the lack of nitrogen 5. And nitrogen 5 you wouldn't expect to be in the state with the low ions. That's probably more around oxygen 6's ionization potential, so like 10 to the 5 Kelvin or something. And the fact that it's missing from there can actually help constrain what's ionizing the oxygen 6 in the first place. But it's not a problem. It's a problem because oxygen 6 can't be ionized in your typical way, photoionization or collisional ionization. You have to invoke something weird, like high mass X-ray binaries or weird radiative cooling flows or something. So, but it's not a problem, I would say.
So you show that the gas is more or less bound to the halo, and that you have the full cosmic baryon fraction, or the cosmological fraction. What do you think is the origin of the metals that we observe in the IGN and things like that? Is it just that at high redshift the picture's completely different?
That's exactly right. Yeah. So I think at high redshift things are drastically different. At least that's the assumption I make. Yeah.
Where did the density and temperature estimates come from, and why isn't the temperature a whole lot higher at these low densities?
So yeah, that's a good question. So basically the temperature and density comes from assuming photoionization equilibrium, and so you've got an extragalactic UV background that photoionizes the gas, and you can do a cloudy model where you model the gas as a uniform slab in thermal and ionization equilibrium. And what happens when you do that is you get a temperature of the gas that comes out of that. And so photoionized gas is typically between about 10 to the 4 and 10 to the 5. Now you can also get temperature constraints by looking at the absorption profiles of the gas and the absorption widths. And those are also consistent. The Lyman alpha widths, the low ion widths are consistent with 10 to the 4 to 10 to the 5 Kelvin gas. Yeah.
Any last questions? Not, let's thank Jess again.